Let's get started with some number theory this morning. Can everyone see my screen?
Yes, please.
Yes.
Okay, so we're going to talk about remainders and modular arithmetic and some applications of modular arithmetic to divisibility today. And we're going to start with something called the division theorem. I think we talked about it once briefly, but we're going to dig in today. So I'll go ahead and state the division theorem. And I'll go ahead and say this is usually called the division algorithm. If you open most math books, this will be called the division algorithm. But I like the division theorem better as a name because it is a theorem. It's not an algorithm. It gets used in a lot of common algorithms like long division or the Euclidean algorithm. So the division algorithm states that for any integer a and a positive integer b, there exists exactly one pair of integers, q and r, and we call them quotient and remainder, such that a equals bq plus r, and r has to be less than b and at least 0. So here's a question. Looking at this equation, what are your first thoughts about it?
It's basically a way for you to work back your divisions and make sure your quotient is the correct.
Okay, that's definitely part of it. That's one of the things that we can do with it. And when you say work back, what Ceylon was trying to say is we're using multiplication, right? We're using multiplication and addition. We're not using division anywhere here. So what's this division thing all about?
Well, usually when you divide and you get a remainder, you multiply your divisor and your quotient and then add the remainder to get your original answer, your original dividend.
If we divide the entire equation by b, it looks more ordinarily like division. We divide an integer a by a positive integer b, and we get q, the quotient, and then we get a remainder over b, the leftover. That wasn't, perhaps wasn't or was equally divisible by b. So here's the thing, we're gonna write all of the integers in this way. And seeing them all written this way, it's gonna help us understand how it is we can do remainder math more easily. So we take all of these integers right here, 0 through 24, and we put them in a 5 by 5 grid. Each one of them is a multiple plus a remainder, multiple of 5 plus a remainder. So let's ask some questions. What is true about the difference between any two numbers in the same column of this grid?
It's a difference of 5.
The differences are multiples of 5. Any two numbers, so we won't just say two consecutive, but the difference between any two numbers. Like if we look at the fourth column here, if we were to, let me see, let me get ready to copy this to another sheet and we'll show that there. We're going to take any two numbers in this column right here and subtract them. And I'm going to go way out. I'm actually going to pretend these columns extend to infinity. They never stop. So two numbers in the first column, maybe 2020 times 5 plus 3 minus 3 times 5 plus 3. What do we get upon subtraction? Oops, sorry, my pen's having a little problem. There we go.
A multiple of 5.
What do we get specifically?
No, 2017 times 5 plus 0.
If we want to, we can add that plus 0 at the end. Good. And plus 0 means we have a multiple of 5, no remainder. So, and this happens between any column and itself. One more example from here. If we subtracted 219 times 5 plus 1. That number is 1096. If we were to subtract 14 times 5 plus 1, which is 71, what do we get?
205 times 5 plus 0.
219 minus 14 is 205 and times 5, but the ones cancel out.
Yeah,
Okay.
so plus 0.
Well, what happens if we subtract any two numbers in different columns?
It will not
the
be a
multiple of
multiple.
6.
It will not be a multiple of 5, exactly. If we take 2019 times 5 plus 1, and we subtract 3 times 5 plus 3, what we're going to get is and that is not a multiple of 5.
Yeah.
Okay. So number 2, okay, yeah, we'll go on. Number 2, what is the smallest 4-digit number that gives a quotient of 219 and a remainder of 2 when divided by some positive 1-digit integer? It's a very wordy problem. How can we approach this?
I think we can start by looking at, like, we can start by writing out the theorem with as much information as we have.
Okay, so I'm going to copy this equation. We want to rewrite things in terms of this identity from the division theorem.
Yeah.
So which one is the number that we're trying to find?
I think A.
A. And that's equal to
BQ plus R.
Can you speak up a little louder for me?
BQ plus
I
R.
can't hear you.
Yeah, BQ plus R. But what, so B is, which one is the number that is the sum positive 1-digit number that we're looking for that I underlined in green? Which one of the variables?
We're looking for B.
Okay, so that's B. And then what's the quotient in this problem?
The 4-digit number. Sorry,
Not
the
the
quotient is 219.
quotient is 219. And what's the remainder?
R, the 1 digit of 2. 2.
Okay, so A equals 219B plus 2. I'll go ahead and write that more simply. Okay, so now let's remember, we're focused on finding a 4-digit number. So how do we get there?
Well, first we can start looking at how we can multiply the quotient to provide us with a 4-digit number before adding the remainder.
How do we do that? What should we pick for B?
The least multiple. Well, you can say by looking at 219 that that let's say you round it to 20. Let's say you round it to 200. You can say that if you were to round it to 200 and then you divide it by 1,000, which is a 4-digit number, you'd have to multiply it 5 times. So then you then go on to multiply 219 5 times. And then you could try it with 4 just to make sure that 5 was the smallest 1-digit number.
Good, I like your estimation technique. This right here is going to be too small.
Five would be the way to go.
219 times 5 plus 2 is exactly right. And that's our answer. So this is mostly a problem just to get you used to working with this equation, thinking about it in this way. It's nicer than division. You know, multiplication is just easier. And in this particular case, well, you know, you can see we're answering an optimization problem, and you can see that we can, you know, kind of estimate to get close. That's what we do in long division anyway.
Yeah.
So now we've got a tough one, number 3. So we have 10 different statements of divisibility. We're looking for those integers that when we divide them by 2, give a remainder of 1. When we divide them by 3, they give a remainder of 1. When we divide them by 4, they still give a remainder of 1. So on and so on up to 11. So 2 numbers that satisfy all these different properties. So what did we learn that makes this a little bit easier?
That
can use
there
our
will
source of
always be
estimation.
a remainder of 1.
What did we learn earlier? So look back up here. Think about problem 1.
There is a common difference between all the numbers in the same row or numbers that are crossing rows.
Right? If 2 numbers have the same remainder when we divide by, let's say, 4. If 2 numbers have the same remainder when they divide by 4, they're in the same column, and we can subtract them and get a multiple of 4. Okay. We can subtract them and get a multiple of 4. So for any 2 of these types of numbers that we're looking for, what do we know about their difference? Let's say that we're looking for one that we call it m and one that we call n. I wrote using n up here, but there's more than one such integer, as the problem states. So we'll call them m and n. What happens when we subtract m minus n?
You get a multiple of n.
We get a multiple of what?
N.
Not n. We're going to have a bunch of statements.
You
Actually, let's focus first just on this. Both of these numbers are 1 more than a multiple of 2. So what happens when we subtract them?
You got a multiple of 2.
That's exactly right. Thank you. The difference is a multiple of 2. Well, Harshita, how are you doing this afternoon? Oh, I can barely hear you. How about Anahita? What happens when we, what else do we know about m minus n?
I'm not quite sure. I'm still trying to figure it out.
Okay. Well, let's look at this statement right here, Anahita. Say both m minus n leave a remainder of 1 when divided by 3. What does that tell us about m minus n? If we arrange all the integers in columns like this, a multiple of 3 plus a remainder, what do we know about the difference between any two integers in the same column? Rishit?
I think it's going to be Q. Wait, no, my bad. The if it's in the same column, it's gonna be a multiple of, yeah, it's gonna be a multiple of Q, and if it's not, then it's not gonna be a multiple of Q.
It's not Q, it's B actually that we're organizing these.
Oh.
But in particular, I'm asking about B equals 3.
So it's it'd be 3.
Yes. Any two numbers that leave a remainder of 1 when divided by 3, when we subtract them, we're going to get a multiple of 3.
Yeah.
And here's an example. 1003, that's one more than a multiple of 3, minus 34. 1003 is 334 times 3 plus 1. The minus 34, which is 11 times 3 plus 1. And the difference is 323 times 3 with no remainder. So m minus n, whatever these two numbers are, their difference is a multiple of 3.
Yeah. Yeah.
So
That
David,
means it's also,
sorry, Manvendra?
that means it's also a multiple of 6.
That means it's also a multiple of 6, and we'll come back to that. Thank you. David, if both of these numbers leave a remainder of 1 when divided by 4, what do we know about their difference?
It's gonna be a multiple of 4.
Good. If they have the same remainder when we divide by 4, their difference is a multiple of 4. And Telvin, if both of these numbers are one more than a multiple of 5, what do we know about their difference? How about Quadwo? If both of these numbers are multiples of 5, what do we know about their difference?
Their difference would be in multiples of 5?
Their difference is a multiple of 5. Good. And we can keep doing this for each of the numbers from 2 to 11. So,
Okay.
what all can we say about m minus n? How do we summarize all this information?
I'm just gonna guess that m minus n is gonna be the LCM of 2 to 11 inclusive.
Yes. m minus n is a number that is a multiple of all these other numbers, 2 to 11. So it must be a multiple of their least common multiple. So m minus n is going to be k times some integer times the least common multiple of 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. Sorry, I've got that crammed in on the right there. So let's figure out what that least common multiple is. Let's find its prime factorization. Well, we've got to have at least 3 powers of 2, at least 2 powers of 3, power of 5, power of 7, a power of 11, Anything else, or are we done?
Well, I don't think we're done. We have to find. Yeah, because M minus we only found. We needed to find the LCM, so we know that that's the LCM divided by K.
What is this LCM? Somebody multiply that out for me.
I'm sorry, but don't we also have a 6 left in there? So wouldn't we add that as well?
What do you mean add it?
To the 2 cubed times 3 squared times 5 times 7 times 11.
6 is not prime.
Oh, okay. We're doing primes. My bad. Sorry.
Oh, well, it's not just that we're doing primes. It's that when we find the least common multiple, this number is a multiple of 6, right? It has a power of 2 and it has a power of 3.
Oh, okay.
I multiplied it. I got 13,860.
I got 27,720.
I get
got
27.
27,720.
Okay, so we've
Oh,
got.
sorry, my bad. I missed the 2.
720. Same, I mean 27.
Okay, so m minus n must be a multiple of 27,720. And the actual problem asked, what is the difference between the two smallest such integers? So what would that be?
Uh, 27,720 because you because K is 1.
Yeah, we just take the smallest possible value of k, plug it in, and we get the smallest difference between any two of all of these numbers. And so the smallest one is 27,721, and the second smallest is 55,441.
Yeah.
Any questions about this? You know, in
Please, can
terms
you
of
scroll down?
Yeah, I'm still not sure about how we got the multiple going down in the column.
like why it is that the difference between two numbers in the same column is a multiple.
I understand that it's a multiple of the quotient, and I understand that part, but I am not exactly sure how we were able to come from our answer using that fact.
Okay, by the way, it's a multiple of the divisor, not the quotient. So
Okay, sure.
That's okay. I just wanted to make sure that everybody begins to get the language well.
Please,
So-
when you did 2a to the power 3, I don't think you added like 2 alone.
Now, Norley, can you repeat that for me?
The LCM, you wrote 2a to the power 3, but you've also written 2. But are we supposed to like add it so it to be 2a to the power 4?
Maybe I'll do it like this. If I said that some number, and in this case it's m minus n, if I said that some number, actually, instead of calling it m minus n, I'll call it x. If I said that number is a multiple of 3 and a multiple of 5, what would you tell me that you know about that number?
It's also a multiple of 15.
Right, it's a multiple of their least common multiple. If I said it's a multiple of 3, it's a multiple of 5, and it's a multiple of 9, then it is necessarily a multiple of what?
90.
Go ahead, Rishit.
135.
90.
Not necessarily.
45.
45.
Oh, yeah.
45.
My bad.
We don't just multiply all three of these numbers. What we do is we make sure that we include their prime factorizations. So by taking just 2 powers of 3, we automatically have that 1 power of 3. Right, so we're just looking for the biggest power of 3. Any multiple of 9 is already a multiple of 3 because 9 is a multiple of 3.
Okay, I get you. Thanks.
So the least common multiple of all of these we construct by using 2 powers of 3 and 1 power of 5, which is 45. And that's what I did up above. I used the greatest power of each prime. 8 has 3 powers of 2, and that's the most that we have. 9 has 2 powers of 3, and then we have a 5, a 7, and 11. And this is why I didn't bother with 6, because 6 has a power of 2 and a power of 3, but we've already got several powers of 2 and 3. Okay, moving on.
Actually,
It's called
Mr. Crawford, I'm still not sure about that part about the multiple. How we were able to use the fact about the common multiple difference to solve the question.
Okay, so what we had was information about, okay, so let's summarize what we did. We know that m and n have the same remainder when divided by 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. What we learned from problem number 1 is that if we subtract them, we get multiples of 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. M minus n has to be a multiple of all those little numbers. So since it has to be a multiple of all of them, it has to be a multiple of their least common multiple. And so we found their least common multiple.
M represent?
Speak up just a little bit for me.
Yeah, what does M represent?
M is just one of these two numbers. I named one of them N and one of them M. Right, I wrote N out right here, but I could have just as easily written M.
There are possibilities.
Yes, exactly. They are possibilities.
Okay.
Okay, so let's take a look at this lesson. I call this Secrets of the Counting Grid, and most of this is just to get us more and more used to thinking this way, with a multiple plus a remainder. And one of the reasons is because multiples are easier to deal with than remainders. The remainder makes things more complicated. With multiples, we can find least common multiples without too much trouble, but if we're told that there are these remainders, well, there's more work to do. We have to figure things out a little more. So okay, we're gonna do something fun here. Okay, hopefully I won't botch this. Let's do these one at a time. Somebody offer me the month, day, and year of your birth. What's your birthday?
July 5th, 2006.
25th December.
22nd December.
Hold on. We're going to do this one at a time. I'm not going to be able to memorize all these. But here's what I'm going to do. I'm going to quickly compute the day of the week on which you were born. And this July 5th, 2006, I believe, is a Wednesday.
How so? I think I thought it was a Friday. I'll check. No, it is a Wednesday.
Oh, good. Somebody else give me your birthday.
December 22nd, 2006.
Everybody wants to volunteer at once. How about Archie? What's your birthday?
February 10th, 2006.
February 10th, 2006. That's going to be a Friday.
Yep.
Okay. And I've seen people who practiced this so much they could do it just instantly. Come up with the day of the week from a month, day, and year. So let's talk about how this is done. So it turns out that I'm going to count for days past Sunday, and I'm going to go back to 1900, the year 1900. Um, December 31st, 1899. Let's see, what day of the week is that? So December 31st, 1899 was a Sunday, as it turns out.
I'll check.
And so if we knew that, what would the date be for January 1st, 1900? What would the day of the week be?
Monday.
Monday.
Okay,
Monday.
it's the very next day. We just add one day. Well, what if it were January 23rd, 1900?
It would be a Wednesday.
A Tuesday.
Tuesday, my bad.
That would be a Tuesday. And how did you come up with Tuesday? Whoever came up with that?
I subtracted 1 from the 23, which got me 22. Then divided it by 7. And I got a remainder of 1. So I just added 1 to Monday, getting Tuesday.
Okay, good. You used a remainder. I'm going to do it a little bit differently. I'm going to add 23 days from December 31st. And the reason I'm doing that is because this number is 23 right here. So it's easier for me to think that way. So
Okay, yeah.
is 3 times 7 plus 2. So we go 2 days past Sunday. We don't care about the total weeks, right? In 1 week, we know it's the same day of the week. So we just forget about that. Okay. What if I wanted to know the date on, or the day of the week on the date, January 23rd, 1901?
Wednesday.
How do you know?
Because a particular day changes by 1 day every year.
Yes. Why does that happen?
Because the number of days in a total year is a multiple of 7. I don't know whether it's plus or minus 1. I've not calculated it yet.
Let's calculate.
Wouldn't that leave a remainder of 1? Because 52 times 7 is 364.
That's right. And so we just move forward 1 day from Tuesday to Wednesday. Okay. So what if I wanted to know the date on March 23rd, 1901?
That would be 31 plus 30 plus I forgot months, my lord. 31 plus 30 plus 23.
Good. Very good. So here's what I'm going to do. I'm going to say that to go from December 31st, 1899 to March 23rd, 1901. Who is that was counting that up for me just now?
Me, Rashid.
Okay, so what Rashid has done here is added separately 1 year and then 2 months, but these are specific months, so we'll come back to that. And also 23 days. We break down the process into 3 pieces. The year piece is 365 days, which is 52 times 7 plus 1. The 2 months are January and February. We go through all the days in January and all the days in February. And January is 31 days, so it's 4 times 7 plus 3. February, February isn't 30 days. It's
28, my bad.
Yeah, it's 28 in the year 1901.
And then the 23 days is 3 times 7 plus 2. But we don't care about the weeks, so we just add up those remainders. So what day of the week is it going to be?
Saturday.
Saturday. So now let's do this for somebody else's birthday. Non-Norley, what's your birthday?
August 8, 2006.
August 8, 2006. So we're going to go forward from 1899. How many years do we go forward?
7 years.
More than 7.
107 years.
107 years. But we're actually not going to go the full 107 years, are we?
No, just 107 days.
It's going to be 106 complete years.
Oh, yeah. So it's 106 days.
So we're going to go for the first 7 months, first 8 days, and 106 years. But here's the thing. Not every year has the exact same number of days.
Yeah, leap years.
We've got leap years. How many of them are we going to have during these 106 years?
25. Oh, 20.
26.
26.
Turns out that we have 26. And it turns out, and some people might get confused about this because the year 1900 did not have a leap day.
What?
But 2000 did, yeah. Every 4th year is a leap year except multiples of 100, but then we add back multiples of 400.
Why?
The reason is because it's not exactly 365.23 days for a revolution of the Earth around the sun. Right? We build our calendar. It's like 365.23, if I recall correctly.
So it makes sense to do it like that. Okay.
Yeah, we build little adjustments into our calendar. So now we add up.
25.
So we're going to add up all the days that pass here. And now the 7 months, that's the toughest thing, right? Because we go through all the days in January, all the days in February, all the days in March, April, May, June, and July. So this is the toughest part. That's a lot of work, right? Whereas we add 8 days here, and then we add 106 plus 106 divided by 4 rounded down, which is 26. So we have 106 plus 26, which is 132. These two numbers, days, and then the number of leap days, that's not as hard as the months. So I'll go ahead and tell you the way that I think about the months. The extra days, if we're talking about a January date, we don't add anything because we're in January, we haven't had a full month yet. If we're in February, we've had 31 days, which has a remainder of what?
3.
3. If we're in March, we've had 31 plus 28 days, which has a remainder of what?
3.
Good. And then April, we've had 31, 28, and 31. So how many
6.
extra? Yeah, 6. 6 extra days beyond a multiple of 7. Then we add 30, and we get up to 8, but I'm just going to call that 1 because 8 is just one more than a multiple of 7.
Yeah.
And then there are 31 days in May, so when we get to June, we're adding 3 more to get to 4. June has 30 days, so we add 2 more to get to 6. And then August, July had 31 days, so August has 3 more than 6, which is 9, but I'm just going to call that 2. And if you want to see the whole calendar list, I'll keep going here. September plus 5, October 0, November 3, and December 5. I call these the monthly adjustments. And they are all just, they're just remainders, right? The monthly adjustment for August, that plus 2, is the remainder when we add these 7 numbers together and divide by 7. If we add those 7 numbers together, we get 212, which is 30 times 7 plus 2. So in total, like, you know, we've gone forward more than 106 years to get to was that non-Orly's birthday?
Yeah.
Okay, we've gone through 106 years, 7 months, and 8 days, and ordinarily all that would look like this: 106 times 365 plus leap days plus 31 plus 28 plus 31 plus 30 plus 31 plus 30 plus 31 plus 8. But all we care about is the remainder when we divide by 7, right?
Yes. Although I have, shouldn't it be plus 25 since 1900 isn't the leap day?
But even though 1900 is not a leap day, the first one is at 1904. The second one is at 1908. It actually makes it easier for us because each positive multiple of 4 gives us the leap day.
Yeah, so then
so how many multiples of 4 from 4 to 104?
Okay, yeah, because 100, I see, because if there was 104 and it was just from 0 to 100, it would be 26, including 0.
Yeah, the fact that we're not counting 0 as a multiple of 4 actually helps us.
Yeah.
So
Please, what did you divide the number of the months by to get the monthly adjustment?
ask that question again.
What did you divide the number of the months by to get the monthly adjustment?
We're always dividing by 7. We're always dividing by 7 and finding a remainder. We just want to know how many days forward we move from week to week.
But when you divide 31 by 7, you don't get 0.
I did not understand that question, unfortunately. Can you ask again?
You said the number of the days were divided by 7. And I was saying when you divide 31 by 7, you don't get 0.
When you divide 31 by 7, you get 3. And that was what we did going from like January to February. We added 3 extra days.
Okay.
And then we added 28 right here going from February to March. And that was adding no extra days, so we stayed at 3 because it's 31 plus 28. And then we have 31 plus 28 plus 31, which is 3 extra days plus 0 plus 3. And that gave us 6.
Okay, thanks.
So the total number of days that we move forward during all this process it looks like that. Total number of days from December 31st, 1899 to August 8th, 2006. But we don't care about all the multiples of 7. We can just wipe those away. And so I call these month, day, and year values. Our month value is the 2. Our day value is the 8. And then 106 plus 26, or 106 times 1, but that's just 106 plus 26 is our year value. And we add those up, and what do we get?
$132 years, 2 months.
I get 142 also. And that itself is 20 times 7 plus 2. So on what day of the week was Non-Norley born?
Tuesday.
That's a Tuesday. 2 days after Sunday. And that's it.
Non-Norley, are you correct?
Yes, yeah.
Okay, so I want everybody to practice this one time, okay? Who's somebody whose birthday we have not done yet?
Me.
All right, David. What's your month, day, and year, David?
December 22nd, 2006.
So what is the month value?
What's the date we're computing from?
December 22nd, 2006. So what's the month?
To find.
Is it 5? Yeah.
It's 5. Yeah, that's our month adjustment right there. And our day value, of course, is just 22. And our year value, well, it's the same year that we've already computed for. And that's what?
You could just call up.
106. 106?
It's 106 plus 26.
Oh, yeah, sorry.
Number of years plus number of leap days. So on what day was David born?
I think he was born on a Thursday. Friday. My bad.
We get a remainder of 5, add 5 days to Sunday, and we get a Friday.
Yeah.
Yep, Friday it is.
And there are people who can do this real quickly. And you know, one way is if you compute these year values a lot, like, 132, well, that's 1 less than a multiple of 7. And you might just forget about the 132 and just call this, 6 or -1 or something like that. 22 is 1 more than a multiple of 7. If you want, you can reduce these to their remainders before you add. And then that becomes easier, right?
Way easier.
Yeah, let's do one more real quickly. Sanjana, what's your birthday?
14th August 2004.
Did you say the 14th of August?
Yeah.
Okay. So our month value is going to be 2. The day value is 14, which is a multiple of 7. So we don't even need to worry about it. It's going to have a remainder of 0. And then 2004, we've got 104 plus 26, which is 130 is the year value. And 132 is 6 more than a multiple of 7. So you were born on a Saturday.
Yeah,
Now,
that's correct.
and so there's one thing about all this that is a little bit tricky. Suppose that Sanjana, and excuse me for misspelling your name, suppose that Sanjana were born before February 29th on this year. We wouldn't add the leap day. So instead of a year value of 130, we could have a year value of 129 with one less leap day if she were born before the leap day. Does that make sense?
Yes.
Yeah.
What if she was born on the leap day?
The one on the leap day, it's just we have, instead of 52 weeks and 1 day in that year, we have 52 weeks and 2 days. So we just have to add 1 for each leap year that went by.
Okay.
So that's why we take the year and add to it 1/4 of that total, round down. Okay, so part of this is to show that computations are easier if we only need remainders, right? Never once did we compute the number of days in 106 years and some number of months. We never did that because that would be tedious. So remainders help us when all we need are remainders. So let's move forward and let's solve some problems. Okay, take a look at this problem. When Rachel divides her favorite number by 7, she gets a remainder of 5. What will the remainder be if she multiplies her favorite number by 5 and then divides by 7? Excuse me.
Won't she get remainders of 4 instead of 5?
How do you know?
Well, what I did was that I looked at a multiple of 7 and I added 5 to it, and I added 5 to it, and then I multiplied it by 5, and then I divided it by 7.
Okay, Rachel's favorite number could be any of these numbers. And we could pick any one of them, like 26. And we could multiply that number by 5.
130.
And I don't care so much what it is as I do what the remainder is when we divide by 7. Does everyone see that?
Yeah. So then.
So in this case, we get a remainder of 4. So whoever offered that answer, you seem to be correct, but is this always going to work? Maybe we can say that Rachel's number is 7 times Q plus 5. And now let's multiply that times 5. We are always going to get a remainder of 4. So what mattered in these computations and what did not matter?
The 25, the 5 by 5 is what mattered. Because
Right.
5 by 5 gives you 25, which is 3 times 7 plus 4. That's where you get a 4 from.
Right. Just like when counting forward, finding what day of the week we were on, that multiple of 7 never factored into our answer. What did factor into our answer was 5 times 5. We only needed to multiply the original remainder by 5 and then reorganize it in terms of a multiple of 7 plus a remainder. Well, that's nice. We can skip the multiple and just focus on the remainder. Any questions about this one?
No.
Yeah,
No.
so yeah, the ending number was 5. So can you just like skip everything and just say 5 squared is equal to 25 divided by 7?
That's right.
Okay.
So now this little lesson is called Exponentiation of Remainders as Fast Counting. Just like Wendy went through fast counting methods with all of you. Here, let's say that we want to know the remainder when 30 to the 5th power gets divided by 7. And we could spend time multiplying out 30 to the 5th power. It's 2,430,000. And we could divide that by 7 and do a whole bunch of long division and spend a whole lot of time. I say we don't need to spend nearly so much time. Why not? Suppose I just said, what is the remainder when 30 times 30 is divided by 7?
Thirty is equal to 4 times 7 plus 2.
Good. How can we use that?
You get a remainder of 2. So if it's 30 raised to the power 5, it means you have to multiply the remainder by itself 5 times.
That's right. Very good. Just like when we were working with weeks before, if I said we're going to go forward 30 days, but we're going to do that 30 times, then we might rewrite this as 30 times 4 times 7 plus 2. But if we only care about the day of the week, for instance, we only care about that 2. So what I'm going to say is this is equivalent to going forward 2 days 30 times. Right? And I write those 3 bars and I say equivalent instead of equal, because 30 times 30 is not equal to 30 times 2, but they are equivalent in the sense that if our goal is only to find the remainder, well, they have the same remainder when we divide by 7. And I'm going to write mod 7, that's short for modulo 7. And that's just a fancy way of saying that we're working with remainders. So the remainder, here's how we write that. We say that the remainder when 30 is multiplied by 30 is the same as the remainder when 30 is multiplied by 2 when we are dividing by 7. So that's how we write that. So we can replace 30 with 2. Well, you know what? If we can replace 30 with 2 and multiplication is commutative, then now we can think of this as going forward 30 days 2 times, and we can replace that other 30 with a 2 also. And then we say, hey, that's just 4 modulo 7. But let's compute. Let's just be sure. Let's check. 30 times 30 is 900. And what is 7 into 900?
128.
With a remainder of 4. And there it is. 4 is, in fact, the remainder. 900 can be rewritten as 128 times 7 plus 4. So now, if we want to know the remainder when 30 times 30 times 30 times 30 times 30 is divided by 7, we can just replace all of those 30s by 2's. And what's 2 to the 5th power?
32.
32.
And what's the remainder when 32 is divided by 7?
4.
4.
Good. 4 is the remainder when 30 to the 5th power, which is 2,430,000, is divided by 7. Does this seem easier?
Very,
Yeah.
yes, it does.
Yeah, very much easier. We can dodge a whole lot of time-consuming computation that way. Now let's use this in some problem solving. Oh, and by the way, those of you, there was somebody who posted on the message board a couple of weeks ago about a problem with triangular numbers and their units digits. Take the lessons that we're learning today and go back and apply it to that problem, and it may be easier now. So here's a problem. In 1963, mathematicians at the University of Illinois used a computer to show that 2 to the 11,213th power minus 1 is a prime number. That's a big, big number. That's like a 3,600 some odd digit number. If this number were written in standard notation, it would contain, they tell us, 3,376 digits, a little bit smaller than I thought. What would the units digit be? So we just want to know the units digit. What's another way of saying we want the units digit?
The last digit.
The last digit? Okay, think of it as a remainder. It's the remainder when we divide by what?
The divisor.
10.
It's the remainder when we divide by 10. Okay, so we want to know the remainder when 2 to the 11,213 minus 1 is divided by 10. Really, we just need to know the remainder when 2 to the 11,213 is divided by 10. And then we'll subtract 1 from that. Let's focus on this big, giant exponential. What do we do to find the remainder when we divide by 10?
Well, we try to find a pattern in the multiplying of 2 multiples of 2 and see if the units digits form a pattern. That way we can decide when we reach this certain digit, this certain square or this certain place, we can say that it's going to have this units digit.
Okay, sometimes we find patterns. Let's see if we do. We're going to play around here. We're going to say 2 to the 1st power. Well, that leaves a remainder of 2 when divided by 10. That wasn't too hard. 2 to the 2nd power is 4. So that has a units digit of 4. 2 to the third power is 8, has a units digit of 8. Pretty easy so far. 2 to the fourth is 16, which has a units digit of 6. 2 to the fifth is 32. But you know what? We didn't even have to compute that. I could say 6 times 2, right? 2 to the fifth is just 2 to the fourth times one more power of 2. And we already know that 2 to the fourth is 6. So we can say 6 times 2, which is 12, which is just 2 modulo 10. So sometimes we can piggyback off of previous calculations. 2 to the sixth is 64, or 2 times 2 modulo 10. We're repeating terms now. And in fact, we're repeating computations before, right? When we went from 2 to the second power to 2 to the third power, we could say, hey, 2 to the third was 2 to the second power times one more power of 2. So we could take that 4 that we knew is 2 to the second power and just multiply by one new power of 2. Similarly, 2 to the seventh power is 2 to the sixth power times 2. Well, 2 to the sixth power is also 4. And then we multiply in an extra 2. So that's the same calculation as before, isn't it? 2 times 2 is always 4. So if we have, or 4 times 2 is always 8. So when we have a units digit of 2, we always know the next one has a units digit of 4. And when we have a units digit of 4, we always know that the next one is going to be 8. And so we have this cycle of 4 remainders: 2, 4, 8, 6, 2, 4, 8, 6. So every fourth term it repeats. So what do we need to do now?
Divide the 11,000 and something number by 4.
Okay, now what?
If there's a remainder, based on that remainder, we can judge what type of remainder it'll have. So first we'll say that if it divides evenly, then we say that it's going to have a remainder of 6 when divided by 10. So we multiply by 10 and then we get 6 as the unit.
But we have a remainder of 1 here. So what are we going to get?
So that means that the remainder in mod 10 is going to be 2.
That's right. Every power of 2 that is 1 more than a multiple of 4 in this pattern will have a units digit of 2. And we can even see a few examples. 2 to the first power is 2. 2 to the fifth power is 32. 2 to the ninth power is 512. 2 to the 13th power is 8,192. So yeah, every fourth one, and these are the ones that are 1 more than a multiple of 4 in the power. So what do we need to do now?
Based on the fact that we now know that it will have a remainder of 2. It'll have a remainder of 2. We then subtract 1 from 2 to find our final answer.
So the units digit?
Yeah, so you're going to have a units digit of 1.
Just 1. We don't have to compute the other 3,375 digits, thankfully, because that would require a whole lot of paper. Okay, let's take a look at problem number 2. Ooh, big number. We have an exponent of an exponent. But we only need the units digit, so we can work modulo 10.
Maybe we could start by finding out a pattern with the units digits, and then we could find out what number this would be and correspond the pattern to the number, the term, like the number which this would be in.
Okay, so maybe we can work with this 7 to the 2007th first and look for a pattern of remainders of powers of 7.
Yeah.
Hey,
No,
man,
but
could you close that door for me?
they're just asking for the units digit. So it'd be 7, 9.
What's 7 times 9?
20,
And it's going to be
26. What am I
going to
saying?
have to
63.
be as the mod.
7 times 9 is 63, which leaves remainder 3. Then we multiply that by 7. 7 times
1.
3 is 21. And then
7 again.
7 again. Yeah, anytime we see that 1, we know that we're about to repeat. We're about to get to some point that we've been before. So we have a block of 4 remainders that are going to repeat. We know it's going to repeat because 7 times 7 is going to be exactly what 7 times 7 was before. 7 times 9 is going to be exactly what 7 times 9 before. It doesn't change. Good. So this repeats for us. So we go, okay, 7 to the 2007th. 2007 leaves, what do we do with that 2007?
We multiply it
Divide
with
by 4.
We divide it by 4. Good. So 7 to the 2007th has a remainder of what?
3. So
3.
Okay. But we're not done yet. We're not done yet. All we've done is found the units digit of 7 to the 2007th power. Now we need to take that to the 2007th power. So what we've done is we've showed that 7 to the 2007th leaves a remainder of 3 when divided by 10. So we can replace what's inside the parentheses by 3. Now what do we do?
We try and find the same pattern with powers of 3 and use that to determine the units digit.
Okay. What is the pattern for powers of 3?
3, 9, 7, 1.
3.
3971, 3971, same units digits, just in a different order. And again, we want the third one, just like we did before, which is going to get us back to 7. So 7 is our answer. So we're going to do this a second time. We're going to use a second methodology here. That was nice. Didn't take terribly long. But what can we do with when we take an exponential to an exponential power?
We can multiply it.
Yeah,
We can multiply the exponents.
we can multiply the exponents. So now I could multiply this out, but do I need to multiply it all out?
Maybe.
I mean, you could just
No,
do it
you
up
should
to the
just multiply
unit.
7 by 7, which will give 49. So 9 would be the unit.
That's not bad. That's not bad. I like that. But I'm going to put it a slightly different way. We just need to know where our exponent is in terms of multiples of 4, right? Because the pattern repeats every multiple of 4. So 2007 times 2007. It is 7 times 7. We could also make it just 3 times 3, modulo 4. These are each 3 more than a multiple of 4. And that's 9, which reduces to 1, modulo 4. So we just need the first number in the sequence, in the pattern of powers of 7. That's it. And that's our easiest solution of all. Any questions about this? Okay.
Please, can you explain it one more time?
Sure. What we want to know is where this power of 7 is in this pattern right here. And this pattern repeats every 4 powers of 7. So what I really want to know is, where is the 2000 times 2007 times 2007th term? The 2007 times 2007th remainder in this list. But they come in multiples of 4. So I can disregard multiples of 4 and just take the remainder when I multiply 2007 times 2007. That's why I did 2007 times 2007 modulo 4 right here, which reduces to just 1 modulo 4. So that exponent is going to be the same in the pattern of units digits. 7 to that power is going to be the same as 7 to the first. We can just replace that gigantic exponent with 1. Okay, let's take a look at problem number 3. Now this one's a little different. Now we're not dividing by 10 anymore. We're dividing by 120, which is much bigger. Can we still find like a pattern? What happens here?
Well, maybe we could try to simplify the value we're dividing by. We could say something like, if we put this into mod 10, it's the same. We can say that the remainder is 0. And so if we divide this number, possibly it might have some correlation with the actual remainder of the actual.
Here's what I'm going to do. I'm going to let you all work on this for a couple of minutes, and I'm going to go refresh my drink. I'll be back in just a moment. I'll introduce you to my second one. This one's a boy. And his name is Ajani. And Ajani likes modular arithmetic. So has anybody come up with an idea for this problem right here?
Well, I've tried something. Well, what I did was that I found out that in mod 10, no matter the power, there will always be a remainder of 1 in mod 10, a remainder of 1 for powers of 11. And then, so I tried to convert the 120 into a power of 10 as well. And it has a remainder of 0. So I divided the remainder of 1 by the remainder of 0. And I found out that the remainder is equal to 0.
I don't know how we can get from mod 10 to mod 120 necessarily. Modulo, two numbers can be equivalent modulo 10, but not equivalent modulo 120. So I don't know if that can give us the complete solution as we multiply. But what we can do is try what we did before. What was our very first strategy?
We looked for a pattern in the powers in mod 10.
Yeah, let's start small and play. What about 11 squared?
1.
It's always going to have a remainder of 1 because you're multiplying 1 against 11 every time.
Ah, how nice. It happens that we're working in a modulus where we find 1 very quickly. So what's 11 cubed?
1, remainder 1.
It's not remainder 1.
The unit digit would be 1.
We're not looking for the units digit. We're looking for what we get when we divide by 120.
Oh, 121.
Is it 11?
So it'll be 11.
It's 11, right. It's 11 squared times 11. And we already know that 11 squared is 1. So we just get 11 modulo 120. So we get 11, 1, and we already start back over at 11 again. So what's 11 to the 4th?
1.
So what's 11 to the 35th?
11.
It's going to be 11, sorry.
Yeah. Within these two that go back and forth, it's going to be the first one. So our answer is just 11. So sometimes even with like a big, nasty, complicated modulus like 120, it's worth doing a little playing around to see if we can still find a pattern. Sometimes we do. Okay, so sometimes I teach some of that lesson without talking about the fundamentals of modular arithmetic, but let's go ahead and talk about congruence. And you can think of congruence as equivalence. Later, as we get deeper into mathematics, these words have different meanings, but for right now, they're fine. They're the same. We're gonna write 53 is congruent to 13 modulo 10. Earlier, we said we write that when it is that these two numbers have the same remainder, right? But here's what we're going to do. We're going to say more formally that two numbers are equivalent modulo 10 when their difference is a multiple of 10, meaning that if we divide that number by 10, that is an element of the set of integers. Has everyone here seen that big bold Z before?
You showed it to us last time.
Yeah, yeah.
Okay, so we've talked about that that is the set of integers, and it could be any integer, positive
Yeah.
or negative.
Yep.
Okay, 53 minus 13 over 10 is 4. That is an integer, so we say 53 is equivalent to 13 modulo 10. Okay. Now, when we write more generally, A is congruent to B modulo M. That means that A minus B divided by M is an integer, and I'm going to give that integer a name. Why might I give that integer a name? Instead of just saying that it's...
So that it's something that's common between the both of them.
Well, I could just say that it's an element of the integers, like I did up there. But if I give it a name, this is like naming the beast, like what we did in order to compute infinite geometric series. If I give it a name, I have an equation. Now I can multiply both sides by M, and I have something that looks a whole lot like the division theorem identity that we learned about, right?
Yep.
And in fact, I could rearrange this and say that A is equal to a multiple of M plus a remainder. Now, B doesn't necessarily have to be a remainder, like 13 up here is not the remainder when we divide by 10, right? But the only difference is uniqueness. The only difference is that we don't restrict B to necessarily being from 0 to 9 inclusive, modulo 10, or modulo M from 0 to M minus 1 inclusive. But it's nice to have an equation because that equation may help us solve some problems. So now let's talk about some properties of equivalence. Now, equivalence is transitive. If A is congruent to B modulo M, and B is congruent to C modulo M, then A is congruent to C modulo M. Do you believe it? Is this a true statement? Both of these are true statements. Can we necessarily conclude that 33 is equivalent to 19 modulo 7?
Yes.
Yeah, how do we know for sure that it's always going to work?
Because if the remainder, because the fact that the congruent just means that you get the same remainder when divided by the modular number.
Okay, so that's our intuitive explanation. That's the way we've built things up intuitively. I'm going to use the definition. We're going to do this in a rigorous way, the way that a mathematician would do it. And here's the way that a mathematician would do it. A mathematician would say, well, if A is congruent to B modulo M, then A minus B divided by M is an integer. Then if B is congruent to C modulo M, then B minus C divided by M is an integer. Now, there's a property called closure. Have you guys heard of closure before?
No, please.
It's not that hard to explain. It's just a new word. We say that the integers are closed under addition because if we add any two integers, we necessarily get another integer. So not too complicated, right? So the
Yeah.
integers are closed under addition, and the integers are closed under subtraction, and the integers are closed under multiplication, but the integers are not closed under division.
Okay.
Similarly, rational numbers are tell me, are rational numbers closed under addition?
Yes. No, no.
Can you name two, Rishit, can you name two rational numbers that if you add them, do not give you a rational number?
No.
Yeah, the rational numbers are closed under addition. And if you want, work it out like this: A over B plus C over D. And see what you get. Are the rational numbers going to be closed under multiplication?
No.
They are.
The rational numbers are closed under multiplication. If you multiply a rational number A over B times a rational number C over D, you get AC over BD. And AC and BD are both integers. So that gives us a rational number by definition. Are rational numbers closed under division?
Well, in some cases, you get undefined or it doesn't work out, so you could say they aren't closed.
That's right. If we divide by 0, we get an undefined, well, it's not defined to divide by 0. Therefore, we don't necessarily get a rational number. Good. So back to what we're working on right now, this transitive property. A minus B over M is an integer. B minus C over M is an integer. So by closure, the sum of these two expressions must be an integer. And if we add these two, what do we get?
A rational number.
Specifically, what do we get?
A minus C over M.
A minus C over M. So we just found out that A minus C over M is an integer. Therefore what?
Therefore subtraction is closed under.
No, we're not proving closure. What is it that we're trying to prove?
That when you have A into A is equivalent to B mod M and B is equivalent to C mod M, A is equivalent to C mod M.
Right. And that's what we know by definition right here. Since A minus C over M is an integer, by definition, A is congruent to C modulo M. So think through that. These two statements gave us this statement. So we went definition to these statements, which gave us a similar statement, and then back to the definition. So similarly, and reflexive property is very easy. A minus A over M is 0. So that's an integer. So A is congruent to A mod M. If A is congruent to B mod M, then B is congruent to A mod M. If A minus B over M is an integer, then the additive inverse of that is B minus A over M, which must be an integer. And then that means that B is congruent to A. So some of these I will leave for all of you to noodle over, but these are basic properties, and I want you to come to grips with each of them and consider that homework. But now let's do some more problem solving. Let's do problem number 1. So how do we know that the units digit is the same thing as the modulo 7 residue? By the way, I want to make this clear in case I haven't talked about it. We started off the day talking about remainders. And now we're talking about residues. When did that happen? What's the relation?
When we switched into
modular arithmetic. I just want to point this out. When we divide 365 by 7, we say that we have a quotient of 52 and a remainder of 1. However, modulo 7, we say that 365 is congruent to 1 mod 7. And so long as that 1 obeys the same rule as the remainder, in other words, it's at least 0 but less than 7, then we call it a residue. Now 365 is congruent to a lot of things, modulo 7. All those integers, 365, 358, 8, 1, those are all equivalent modulo 7, but the only one of those that is a residue is 1. So residue is kind of like remainder, just thinking in terms of modular arithmetic. So want to make sure that everybody understands that terminology.
So what's the definition for a residue?
Well, that's it right there. A residue is every integer in a modulus, modulo m, is equivalent to 1 residue, which is at least 0 and no greater than the modulus. If I were to write this more like a definition, instead of 1, I would have r most generally. But it's going to come from that exact same equation right here. It's just that we call it a remainder when we write it in equation form, and we call it a residue in modular arithmetic. So here in this problem, I want somebody to explain why is it that the units digit of an integer written in base 7 is the same thing as its residue, modulo 7.
Because you get the units digit of digits of a number in base 7 when you divide let me put my words together. The units digits of a number in base 7 is the remainder when you divide it by 7, which is exactly the definition of a residue.
Well, the question is, how do we know? How do we know that the units digit is the remainder when we divide by 7?
Well, no matter what, 3 is going to multiply 7 to the power 0 and give you 1, which is going to give you always add on 3. So if you're always going to be adding on 3, no matter what, no matter how many times you divide it by 7, there'll be a 3 left over due to that fact, because it's always add on 3.
I'm going to do it like this. I'm going to take everything to the left of the units digit and point out that that is a multiple of 7. So now I've written this using the division theorem. I've written it as a multiple of the divisor 7 and then plus the remainder 3. And that tells us that this number 323 base 7 is congruent to 3 modulo 7. Say it's equivalent to that, and then that is equivalent to 3. To make that clear. More generally, if we were to generally write a number in base 7, and this is actually kind of a hard thing to do, it looks kind of clunky. If we have a k-digit integer in base 7, that k-digit integer is equal to each digit times power of 7 then we get all the way down to the last digits. But most of these are multiples of 7. So we can rewrite this as that part winds up being all that we care about to determine the remainder when we divide by 7. And I know this it seems a little bit tedious. It's something that, you know, you'll grow familiar with it. You'll see this kind of general form more and more as your algebra skills improve, as you get more comfortable with your algebra. You'll read it more easily, you'll absorb it more easily, and you'll understand why, you know, a little bit more at a time, why this is the best way to think of it. It gives us a rigorous proof of what we're trying to do rather than just relying on our intuition that we were starting with at the beginning of the day. It's good to have both. It's good to have the rigor and it's good to have your intuition. Your intuition will help you more with the problem solving. Your rigor will allow you to build more and more interesting theorems as we go and to learn to, you know, write proofs. Okay.
So, Mr. Crawford, basically,
Yes.
the explanation is that when you break it down, the base 7 number, the part of the entire equation will be divisible by 7. So you'd have whatever your final digit multiplied by 7 to the power 0 is as your residue.
Yeah, all the rest of it will be 0 mod 7 because it is a multiple of 7.
Okay, thank you.
Okay, let's take a look at this one right here. This is a problem from the American version of the contest that you all took to qualify for this camp. Suppose that n is the product of 3 consecutive integers, and it's divisible by 7. Which of the following is not necessarily a divisor of n? Okay, let's list everything that we know about n. Well, what do we know about the product of 3 consecutive integers?
It's factorial.
I'm going to let you all play with this for a moment. Try some different values of k.
All the consecutive integers so far, they are divisible by 6.
Okay. Is that always going to be true?
Well,
I will call this our conjecture. A conjecture is the best guess that we can offer, that we want to study and see if we can find out, if we can prove that it's true. So it's divisible by 6, and I'm actually going to break this into to 2 pieces. Something that is divisible by 6 is divisible by 2, and it's divisible by 3. We're kind of breaking down the idea of divisibility by 6 into its component prime pieces. And this is technically something called the Chinese remainder theorem, but we're not going to worry about that level of rigor at the moment because I'm sure you can see this intuitively. Something is a multiple of 6 if and only if it is a multiple of 2 and a multiple of 3. So how do we know that the product of 3 consecutive integers is necessarily a multiple of 2? What are the integers modulo 2? If I were to rewrite all the integers that I just listed modulo 2, what would it look like? Just replace these numbers with residues.
Well, a -3 would be I think it's 1. 1. So it would be 1. Then 2.
Be
Oh,
zero.
sorry, not 2.
Negative 2 will be 0. 1, 0, 1, 0, 1, 0.
Yeah. So what do we know about the product of any 3 consecutive ones of these?
It's going to be equivalent to 6.
Well, just modulo 2 right now.
Well, it's going to give you 0.
Right. Yeah. The product of 1, 0, 1 or 0, 1, 0 is going to be 0 modulo 2. And if we really wanted to be sure, if we wanted to write like a really rigorous proof, we could say if k, we'll use k up here, if k is congruent to 0 mod 2, then this product is obviously 0. If k is congruent to 1 mod 2, then k plus 1 is congruent to 0 mod 2, in which case the product is still 0. So yes, the product is a multiple of 2. And how do we show that the product is a multiple of 3?
We put them in mod 3.
Yeah, we put them in mod 3, and we can go through cases. We'd say, well, if k is congruent to 0 mod 3, then the product is 0 mod 3. If k is congruent to 1 mod 3, then k plus 2 is 0 mod 3. If k is congruent to 2 mod 3, then k plus 1 is a multiple of 3. So in all 3 cases, the product, one of these 3 factors is 0. So their product is 0. Therefore, the product is a multiple of 3. Any questions about that?
No.
So, go ahead.
Oh, no, I was just saying I didn't have a question.
Okay. So now what we know about n in this problem is it's a multiple of 2, it's a multiple of 3, and it's a multiple of 7. Two divides
So
in.
Crawford, would we put each of the numbers into mod 2 and mod 3 to find out whether there are possible was it divisors? Yeah, whether there are possible divisors. And if it doesn't match at least one, if it doesn't match mod 3 or mod 2, then we say that it is not a divisor.
I apologize. I was fixing a writing error of mine. Do you have an answer yet?
Yeah, I was going to say 21 because if you put it into mod 3, it works, but if you put it into mod 2, you get a residue, and you're not supposed to get a residue of 1. You're supposed to get a residue of 0 if it works in the consecutive integers rule.
Okay. I think you're confusing yourself a little bit. We used modular arithmetic to help us build this list of divisibility facts. But let's leave modular arithmetic behind. Divisibility is simpler. When we're dealing with multiples and divisors, we already have a lot of tools at our disposal. It's easier than dealing with remainders. We deal with modular arithmetic because we have to. But here is what we know about n. N is a multiple of 2, n is a multiple of 3, and n is a multiple of 7. Do we know that n is a multiple of 6?
Well, we can say that since 2 times 3 is 6, we can say it's a multiple of 6.
Right. N is a multiple of any common multiple of 2, 3, and 7. Is n a multiple of 14?
Yes,
How do you know?
because
That's
it's
2
7
times
times 2.
It's a multiple of 2 and 7, right? Is n necessarily a multiple of 21?
Yes, because of
Yes.
3 times 7.
It is a multiple of 3 and it is a multiple of 7, therefore it is a multiple of 21. Is it necessarily a multiple of 28?
Yes, because a
No.
multiple of 2 and 7.
Well, a multiple of 2 and a multiple of 7 is necessarily a multiple of
No.
14. But is it necessarily a multiple of 28?
No.
No.
We do not know that it is a multiple of 4. We know that it is a multiple of 1 power of 2, but not 2 powers of 2. That's going to be our answer. And we do know that it's a multiple of 42 because the least common multiple of 2, 3, and 7 is 42. So we use modular arithmetic here to build up our divisibility facts, and then we use our divisibility facts to solve the problem. Okay.
Mr.
No,
Crawford,
yes.
do we necessarily have to use modular arithmetic? Because we already found 6, and we already broke it down 6 without using modular arithmetic. So couldn't we have just done that from the get-go instead of going into modular arithmetic?
Well, we used modular arithmetic in our proof that this was a multiple of 6.
Okay, so it's not necessarily something we need. It was just part of the proof.
Well, I mean, it depends on what you mean by need. If you decide that you can think of this, this product k times k plus 1 times k plus 2, if you can determine that that is a multiple of 6 without modular arithmetic, that's fine. I don't know what the proof would be exactly, but the modular arithmetic proof where we go through the casework is relatively easy. And to me, it's a rigorous conclusion.
Okay, thank you.
So now, okay, we'll finish the day with one real challenging problem here. So this is a tough problem here. I've given many bright students this problem before for sometimes 15 or 20 minutes at a time. And I've seen a lot of people not solve it or get wrong answers along the way. But I want to point out that this problem begins to get much easier when we start thinking about all of these numbers as multiples of 7 plus a remainder, and to group them by what we call residue classes. All the numbers in the same column have the same residue, modulo 7. And what we want to do is we want to build. We want to know the number of elements in the largest subset. We want to build the largest subset so that no two elements, no two numbers in that subset have a sum that is a multiple of 7. Okay, so how do we avoid getting a multiple of 7?
You divide by 7.
Divide what by 7?
The number of elements in the subset.
What does that give us? What would that tell us?
So we could add up the total number of multiples of 7 that we can have. And then after finding out the total number of multiples of 7 that we can have, we could subtract that from the total number of integers in the subset, and to give us all of them other ones which are not divisible by 7.
I'm not sure I understand. Here's a question. Can we have more than one multiple of 7 in the set?
Yes.
No, else if you had to add those two, you get a multiple of 7.
That's right, David. If we have two multiples of 7 in the set, their sum will be a multiple of 7. So we can only have at most one multiple of 7. Here's the big point that I want to make. We can view each of these columns just in terms of their modulo 7 residue. Suppose I have an element that leaves a remainder of 1 when divided by 7. One of these. What could I not include in the set? What could I add to 1 to get a multiple of 7?
A multiple of, we know, sorry,
6.
6.
6, right. Right. 1 plus 6 is 0 mod 7. And that would be bad. So what does that tell us about the numbers that we can put in this set together? Suppose I have the number 22 in the set. What could I not put in the set?
Six.
Right. Can't put 6. Can't put 13. Can't put 19. I can't put any number in that column in the same set with 22, or else we'll have a sum that is a multiple of 7. So if we have, I'm going to name these columns. Call them column 0, column 1, column 2, column 3, column 4, column 5, column 6. If I have a number that is in column 1, I cannot include any numbers from column 6. If I have a number that is in column 6, I cannot include any numbers in column 1. So now, are there other restrictions that are like that?
Yes.
Well, it depends on the combinations. So, like, if you can't put a number of 6, but if you put a number in the column with 3 after, then you can't choose a number from the column of 3.
Oh, we can. We can put 3 and 10 in the same set. What could we not put in a set with 3?
4.
4. 3 plus 4 gives us a multiple of 7. 2 plus 5 gives us a multiple of 7. So if we include any number from column 0, we can't include any other number from column 0. If we include any number from column 1, we cannot include any other number from column 6, and vice versa. If we include any number from column 2, we cannot include any other number from column 5, and vice versa. If we include any number from column 3, we cannot include any number from column 4, and vice versa. So now we want to build the biggest set that we can. What do?
Well, what if you were to say you picked 2 from 2, and then you picked 1 from 3? Would that still work, or would it also mean that
The question says such that no pair, meaning only 2.
Good. 2 plus 2, 2 plus 3, those are all fine. So now what do we do to form the biggest set that we can without having one of these things happen? Would you rather pick numbers from column 6 or from column 1?
1.
How come? What's the difference between column 6 and column 1?
The values of the number in column 6 are bigger than that of the values of the numbers in column 1.
But we don't care about the values. We're just trying to make the biggest subset, so we want the most numerous. Which column has more numbers, column 1 or column 6?
Column 1.
Column 1 has one more number than column 6 because the last number that we put in our set is in column 5. So what we want to do is we want to include all numbers in column 1, right? They're not going to add with each other to make a multiple of 7, so we can just choose them all. They all behave the same when we add them to another number, modulo 7. So we might as well pack them in, include as many as we can. What else do we want to add to our set?
1 number from column 0.
Good. We want 1 number from column 0. We want all the numbers from column 1, which is 287 of them. What else?
All the numbers in column 2.
Good. We could have chosen column 5. Why did you choose column 2?
Because column 2 has more numbers than column 5.
It actually doesn't have more numbers, but it has the same. So we're fine with that. So we can include one number from column 1, all the numbers from column 2, and
All numbers from column 3.
all numbers from column 3. And again, we could choose column 4, same number of terms. And so in total, what we're going to get is 3 times 287 plus 1, which is, I think, 862. Somebody can check my arithmetic.
Yes, correct.
So this is a very tough problem to think about before you think of all the numbers in these columns as being the same. And that's what I want you to realize about modular arithmetic, is it allows us to think of all these numbers as the same for the purpose of a lot of computations and a lot of thinking. And we'll go ahead and call it a day. We'll finish the rest of this document on Wednesday. And I hope you all have a good couple of days studying math, and I'll see you then.
Okay, thank you.
Thank you.
You're welcome.
Well, Mr. Crawford, doesn't mean that
Thank you, Mr.
a
Crawford.
residue is simply the remainder of a modular arithmetic.
For the moment, remainder and residue are essentially the same. There's a tiny little subtle difference, and we'll get to that a little bit down the road. But for right now, for any purposes that you're going to be using this for, you can think of them as just the same thing. Residue is remainder.
Okay, but I have a question that I'm not so sure about. How are you so sure that the number of elements in column 2 is the same as in column 5?
Oh, how do we know that the number of elements in column 2 is the same as in column 5? Because we form the elements in column 2 by adding 0 through 286. We multiply those by 7 and then add 2. We do the same in column 5. We do the same thing, except we multiply 0 to 286 by 7 and add 5. But we have the same quotients, 0 to 286, that we use to construct those numbers.
Mr. Crawford, last week you were talking about how to find the squares of numbers ending with 5, like big numbers ending with 5. And I was asking that, could you use the same thing? For instance, a number like 19, you just square the 9 and write 81 and then. Unfortunately,
it doesn't work. We will find other methods though. Maybe we'll do that later in the week. Maybe I'll make a video to help us with other methods. But 5 is special. And the reason 5 is special is because I'll show this with 35, which is 30 plus 5 squared. When we expand that, kind of like x plus y squared is x squared plus 2xy plus y squared. The reason 5 is special is because it multiplies with that 2 to make it 10. And so we get 30 squared plus 10 times 30 plus 25. And that 30 squared is really, wait a minute. I could write that as 3 squared plus 3 times 10 squared, right? Factor out 2 powers of 10, factor out 2 powers of 10. And then 3 squared plus 3 is 3 times 3 plus 1. but that depends on putting this 10 together from that 2 and 5. So that's why squaring numbers that end in 5 have a nice shortcut that's not available to other units digits.
Okay, thanks.
You're welcome. All right, see you all Wednesday.
About the question I was asking, does it mean that the number of elements in column 3 are the same as those in 4? Because it's also from 0 to 286.
Yes, the number of elements in set in column 3 is the same as the number of elements in column 4. That's correct.
Okay, thank you so much for the class today.
You're welcome.
Thank you.
You're welcome.